Welcome, everyone. My name is Ana Paula, and I'm here for the first episode of the Galvanizing on the Edge, the podcast where we explore the science and the operational insights behind the galvanized steel production. Today, we will focus on one of the most critical challenges in any continuous galvanizing line, which is controlling zinc coating weight and what is the understanding behind of the air wiping process. To guide us through this, we are joined by Michel Dubois, a highly respected expert in the galvanizing operations, who has spent decades of researching, developing, and troubleshooting zinc coating weight consistency and its metallurgical reaction within this process. In this episode, we will especially go through breakdown practical fundamentals and the things that are not always in textbooks, but will determine how a real coating weight can be everyday controlled on the lines. Michel, welcome.
Hello, Anna. Good morning.
Good morning. Michel, welcome to the podcast. And we know that many people, they know your work, they know who you are, but they don't know exactly how you got involved into the galvanizing process. Can you tell us more about this?
Yes, of course. Indeed, I've been hired in 1981 by Phoenix Works. Phoenix Works is a company who had already 5 galvanizing lines. It is located in Ivoramé, close to Liège, and now it belongs to Arcelor, but with not more 5 galvanizing line. Initially, I've been working in tin plate, but I spent there only 1 year because I've been asked to join the R&D group of galvanizing. And at that time, just to give you an idea, they had just implemented nozzles, air wiping nozzles on 3 galvanizing lines, because previously wiping was done with KG rolls. So it's very long time ago. We had no pot management. Nothing was known about dross. Automotive was not the main market. It's a very different situation as today. And indeed, I had the chance to read 2 excellent papers that I recommend to everyone because they are quite old and it was very innovative. There were one of Thornton and Graff and another one from Ileden, were 2 researchers from Australia and Aka Steel, I think. And so they described the physics of air wiping, and just I start piling up the equation manually during my spare time. Just to give you an idea, at that time there was no computer. Everything was done on papers. So it's very different from now, very different. Wiping was not my major task. I had other activities.
Really?
Looking at the zinc adhesion problem, because it was a big problem at that time. And after that, I've been involved in the development of the one-side coating, because Phoenix Works had a special pattern of that, and also later on in the construction of the Segal line that now belongs to Tata Steel.
Yes.
This has been done under the Nippon Steel license, and they had already a very special nozzle, very sharp. They published also a lot of work on this. But in 1987, we have decided to subcontract the research to Von Karman Institute. Maybe some of you know them. They are specialized in fluid dynamics. And this research continued during about 15 years. We wrote the first wiping models I think it was in 1989. I still have the copy of that. And I'm still using it also because it solved the Navier-Stokes equation and gives you the full zinc profile on the wiping. But after that, it was not only coating thickness. We looked at the problem of edge buildup, weaviness, full splashing. Most of the work is published and you can find it in literature. And when I joined CMI, now John Cockerill, I had the chance to use Fluent. Fluent is an excellent software that helps you to have your own lab and to test very new configuration without hardware. So indeed, I've already been involved in R&D, but not research and development in lab only, very in close link with the industrials, talking with operators, making also experiments online and so on. I think this really summarize my background.
It's great. Thank you. Now we go for the more technical part of our conversation. And I would ask you to please share the slides you have prepared for today.
Okay, so it's a long story for this.
Yeah, looks great. So, Michelle, you told us a nice and beautiful story about yourself, but because you're speaking about coating weight, can you tell us why is coating weight and its control so important for the galvanizing process?
Yes, of course. It's really balance between cost and corrosion resistance. No, of course, zinc is on the steel sheet to improve the corrosion resistance. And as soon as zinc is dissolved, and this takes a certain time, steel start to rust. If the coating is not uniform, like on this roof, you'll see the areas with a thinner coating will dissolve much faster than the rest. On this typical picture, we can see that the coating weight was varying along the sheet, with this refer typically to a strip vibration issue, and that's because the coating was not uniform. It was much lower where the steel is already rusted. But on the opposite side, of course, zinc coating has a significant cost. You know that zinc is today cost about 3,000 euro per ton. And if you look at the cost of this coating per ton of galvanized for different coating thickness, you see that the thinner the coating, the higher will be the cost. This is obvious because you have more square meter when you are running thin sheets. And you can clearly see that the difference between 10T and 10 micron is significant. So it's really that. And just to give you an idea, if you are considering that 1 gram of zinc per site on 1 ton is 600 square meter, but the cost is typically 4 euro per ton. That's is it high or not? But just as comparison, annealing costs about 10 euro, not more than that. So you see that improving the heat yield on furnace is not easy, but saving 1 gram becomes really interesting. And also the fact that the final customer is willing to receive a minimum coating weight. So how can you assure that in an industrial process, you always give a coating that's over the minimum value, but is well known? You have to take the mini value that is required by customer, and you have to add 3 standard deviation. Just to give you a very simple calculation, 100 gram, that is the minimum that you have to fulfill. Standard deviation 3%, and believe me, it's already good. Target online will be 109 gram per square meter. So it's significant. The case of galvanneal is different, because in galvanneal, the coating weight variation impact the powdering resistance and also the color of the coating.
So now we could clearly understand how much money is involved the application of zinc onto the strip and the importance of controlling the coating weight. And we know that we do this via wiping. Can you tell us more about what are the main parameters behind the wiping process?
Yes, I can. So the factors that affect coating weight are related to remove a liquid. Wiping is nothing else than removing a liquid. Of course, you have to keep in mind that if the strip makes some intermetallic, and especially thick intermetallic in the pot, that they cannot be wiped. This is why galvannealing is more difficult to wipe than galvanized. In GI, where aluminium is typically over 0.2%, the intermetallic is very thin. It's about 0.1 micron, not higher than that. So it means it has no impact. So there is no effect on steel roughness, at least on coral sheet. This has been proven by different research people. But we have to keep in mind that temperature has a significant effect on liquid viscosity because it's a question of liquid viscosity. I just made for you this type of comparison, the effect of aluminum on this site on the viscosity. You can see that 20 degrees difference in the pot temperature change the viscosity significantly, even more significantly more than aluminum is doing. If you compare 0.15 to 0.3, that's already a big variation in industrial line. The variation of viscosity for the same temperature is very low. That's it.
Thank you. And when we speak about the zinc bath, where is the area where the strip will pass through and be in contact with zinc, and the coating weight again, we've seen that this is basically the heart of the hot dip galvanizing. Can you then explain us in simple terms how does the air knife remove the excess of zinc from the strip?
Yes. Indeed, the wiping process is very simple. It's very simple. The strip is moving out of the pot here, and so you entrain by viscosity force a certain amount of liquid, and you have to apply some external forces on that layer in such a way that the excess is going back to the pot. So this is only a force balance, and this can totally be solved by the Navier-Stokes equation, but we immediately see the main parameters. On one side, of course, line speed and viscosity will have a major effect. And the external force that could be, for example, magnetic force or impact pressures, adjust the final thickness. Magnetic has been investigated by different research labs, but this is not well working. That's why today everybody is using indeed air nozzles and wiping nozzles. And if I want to make a quick sketch of the phenomena involved, of course, the excess of zinc has to return to the... So it means that, of course, the mass flow in each cross-section is identical. So it means that here we have a certain velocity profile of the liquid zinc entrain. The gas here exit the nozzles in speed in the range of 150 to 330 meters per second. It's very, very fast. And because this gas flow impact here a plane, it generates a pressure gradient. And this is the reason why it induces wiping, really, as well as a shear stress. And the shear stress is because the airflow is going along the surface. So you need to solve only that, and that's it. You know what is a final coating thickness that is here, final thickness here.
Thank you. And Michelle, so there's a lot of physics behind the way the amount of coating weight is controlled and measured, not measured, but controlled onto the strip. But what can we expect in terms of defects? Can you tell us what are the not expected defects during wiping?
So the main problem in wiping is those that I just described here. Indeed, wiping is very simple. It's very efficient, it's cost effective, and low maintenance process. This means that this process will not be changed or replaced in the next future, even in a long future. That's my personal thinking. So the main inline issues are nozzle clogging, edge overcoating, splashes at high speed, and of course mechanical problems. This describes, for example, a typical splashing issue that occurs over certain line speeds. I publish a lot of this. This occurs when you are running 180. Here is typically what could happen on the edges. And here are a lot of splashes and so on with the flow here on the zinc layer on the pot that could be different on each side.
Interesting. And now, can you tell me more about the coating uniformity and the challenges behind it? What are the typical causes of coating weight variation from the edge to the center?
Well, when you know the physics, you can solve Navier-Stokes. Navier-Stokes is quite difficult. You can simplify. I like typically that very simple formula here that's coming out of the Navier-Stokes. It's not 100% valid, but it's so easy to use that is, you can identify all the root cause of variation. So the coating weight, final coating weight, depends on nozzle to strip distance, depends on speed, depends on the piping pressure and nozzle opening, because this impact directly the force that are induced by the air nozzle. So indeed, the variation, the total standard deviation, are already discussed, could be from non-parallel nozzles. I mean, the nozzles are not parallel to the strip. Also, it could depend on the strip shape. And what do we have in strip shape? We have crossbow, because in that case, the nozzle to strip distance vary. It could also be related to the nozzle opening. Sometimes the nozzle could vary along its length, I mean. And we have other issues that are minor. And finally, we have the instability in the wiping pressure here, or the strip vibration, because strip vibration is related immediately to nozzle to strip distance.
I understand. And we see that many lines, they've suffered with coating weight issues like edge buildup or other issues that are also connected to some more difficult steels, like advanced high-strength steels, and the way they will perform in terms of crossbow and shape issues. Can you advise us in terms of how to minimize those defects in our lines?
Yes, I wanted first to remind you the key parameters. As I said, it's exactly the next of what I said previously on the previous question. Of course, the key is nozzle opening. It's not always easy to have a constant nozzle opening on a 1 or 2 millimeter. The nozzle to strip distance, it's clear. And keep in mind that the nozzle to strip distance, of course, depends on strip vibration, as I told you. And it depends also on the line adjustment. And the typical distance is between 5 and 30 millimeter nozzle to strip. Line speed. Every time you change strip thickness, of course, due to the heat cycle, but you have to change the line speed. And finally, wiping pressure. That, of course, must be stable and uniform along the nozzle. And as far as why do we have edge buildup, for example, this is because where the strip is not, the two nozzles face each other. It means that this is never stable, so they flap this way. And because of that flapping outside of the strip, you have a drop in the wiping efficiency, and this induces immediately dross buildup. So how can you solve that, for example? It is the baffle. And I like especially two excellent papers where you can find a reference here at the bottom. It is not new. Those ones are Korean guys that have investigated at the lab the coating weight variation versus the nozzle to strip distance. And without edge baffle, the coating thickness on the extreme edge can be as high as 50% more. And I verified that myself also online. And as soon as the baffle, that's only a simple plate, it's just to avoid that the two nozzles face each other, but it decreased significantly. The question is always, how far should be that plate located from the edge strip? And this is more or less given by this excellent Chinese work that, well, they work by CFD, but I am sure that it's absolutely correct. It shows here the optimum distance versus the air gap range, and it means on practical standpoint, practically that you have to be lower than 5 millimeters away from the strip edge to really minimize the coating over thickness. That's it.
Thank you. And when we speak about the strip vibration, how does strip vibration influence the wiping? And what do you see as the standard ways to reduce this issue?
I forgot. So what I've explained to you is what happens indeed at high speed, but low speed is a totally different situation. Fortunately, I have not the time to explain you the details of that. You can find some in my last papers. But you see, as soon as you are running below 60 meters per minute or 50, the backflow here going back to the bar, makes this type of oxide. We have a lot of pictures that show here what happens. And this induced indeed an overcoating that is not located at the extreme edge.
Uh-huh.
I just characterize this piece of sheet with a permascope, and all the numbers you see here are in the thickness measurement by the permascope. You see that here the coating is, for example, only 33 microns when it's more than 100 at this location. So the overcoating is totally different, totally different. Right. Okay.
All right, thank you. So we see now we spoke a lot about edge buildup, the importance of the baffles, and so on. But can you also tell me how can the strip vibration influence the wiping process? And are there any standard practices in how to better control those issues?
The question of strip vibration is not as simple. It's a simple word, but complex situation. Because vibration means indeed variation of nozzle to strip distance. And you immediately see that because they are too proportional, 10% variation of distance give you 10% of variation of coating weight. It means, and when the distance is only 10 millimeters, it means the variation of distance by 1 millimeter, this means 10%. But there are really many types of vibration, so different causes. You can have, or they are moving parallel, or it could be like this one. I mean, the vibration could be that one. It could be this one. They are very, very different types, and I invite those who are suffering from those type of vibration to clearly look at how it is. This is usually pot rolls, bearings, cooling tower, and strip shape. This is typical, for example, in case of too low tension in the center. It vibrates this way. And also you need to identify the frequency involved. I made a paper about at the Galvanizers 2012 to invite people online to look what happens. You cannot only name vibration. It's too simple. Okay.
Okay. And now let's go back to the zinc pot. Can you tell me what is the role of bath dross or any surface contamination that we would see on the bath in terms of affecting the coating quality and the wiping
So what is the impact on wiping? Dross are usually intermetallics. There is, I don't like that we use always the word dross. Dross for me is Fe iron zinc intermetallics. Could be Fe 12.5 or FeZ10. But what is really entrained for me is more oxides. It is more related to skimmings. So big oxide and dross are usually pushed back to the pot because we have a high gas flow. On the previous pictures that I showed you, you see on this one, for example, the reason why we have the skimming that are contacting the strip on one side and not the other is related to the pot walls. Very strange, but it is indeed that one. And if on this side we have no dross or sticking to the rod, it's because the gas flow that's going down, of course, is pushing the dross away. So, of course, pot management has an impact on surface quality. This is where where it's very important to control that. The question of low speed is a bit different. It's a little bit different and need to be addressed differently.
Okay, good. But still in the zinc bath, in the zinc pot area, we spoke about how its intermetallic particles could affect coating weight. But we also know that we have to control the amount of aluminum and the iron in the bath. Let's suppose that the aluminum levels drift. How would this influence in terms of the coating weight thickness?
For me, aluminium is not a major, it does not impact really the final coating weight. As soon as it's higher than 0.18, because the intermetallic is very thin, of course, and because we have seen on previous slide I showed you that aluminium has a limited effect on viscosity. It's not going to have any effect. Of course, if you are running 3% aluminium, in the zinc magnesium issue is different. Galvan is also different. I'm talking here about galvanizing. Of course, below now 0.18, The situation could be different, and it depends also on the entry strip temperature, because in that case, we make an intermetallic, and that intermetallic can be thicker. And this is already solidified piece, so it means it cannot be white. On the opposite way, bass level from my research has never been shown to impact the final coating weight, as well as the location of the final stabilizer roll in the pot. Wiping height also has no effect, except sometime on very thin sheets, because you could have a thermal effect. If you are wiping too far away from the pot, of course, strip cooling on his path from the pot to the nozzles will of course be higher because of time. And in case of very thin sheets like 0.2 or 0.3%, 0.2 to 0.3 millimeter, this could decrease the strip temperature. It means increasing zinc viscosity, and it will impact that.
Okay, so now the zinc is already applied onto the strip, is solidified, and what we can expect in terms of defects to be possibly present onto the coating by itself. Can you show us some examples of surface defects typically occur onto the galvanizing line during wiping?
Of course, I have a collection of some defects, but you have to keep in mind that the defect you see on the final galvanized sheet is a combination of wiping and solidification. Sometimes it's not always easy to be sure which one is responsible of what. So quite well-known defect is a cloudy aspect. You see those type of clouds that we have in the surface is typical of air wiping. That's why to solve that problem, nitrogen wiping has been used. We have the question of ripples. There are different types. This is typical ripples on thin sheets. It's related to the fact that in the gas flow is not stable. It vibrates this way. And because of that, it's making those type of ripple and waviness. This one is typical of low speed. You see what is it exactly? But it is, we have this type of comet shape. I think it is related to oxide that are formed and that impact, the backflow going back to the strip. The question of overcoating, it could be on the edges, but it could also be in the center of the strip. For example, in case of nozzle clogging, it's going to make a ridge on the... And why is it like that? Because you have overcoating. All those overcoating piles up during rewinding the coil, and unfortunately, the final customer never complains about variation of coating weight, but it complains about strip flatness, because as soon as you decoil, the strip will be more deformed at that location and make waves at that. We have the full splashing that typically occurs at high speeds, as I told you. I don't know many people who are suffering from that, but all those who want to reach 200 meters per minute will for sure observe that defect. We have the edge effect, also related to low speed, as I told you. It's mostly due to the backflow that's coming back to the strip. This one is maybe not as clear. It's a typical coating weight variation. You can see in the picture here, they are dark and bright areas. This is because of strip vibration. But considering the pitch that we see here, most probably it's related to pot rolls. We have, in case of spangled material and heavy coatings, this heavy coating, it is 40 microns zinc coating. We have those dendrites. It means that the solidification is not straight. The spankles are very long. We have also this one with mustache. Those two are really, it's a combination of wiping and solidification. This one is not 100% understood by myself. You see how it starts, exit of nozzles, and we have, of course, the edge overcoating that I already discussed previously with you. That's one of the major defects.
Can we say that the dendrite defects and also the mustache ones are more correlated to GI coatings?
Of course, this one is related to GI with spangle. In
with
case of
spangles?
non-spangle material, you have different defects
Mm-hmm.
because very strange. If you remove antimony and lead from zinc, you see new type of defect. They are more sensitive to other type of defect, and the reason is unclear. I think it's related to oxidation, but it is not very clear. The moustache is very typical of heavy coating zinc magnesium and
I
also
see.
of GI. That's clear. It's a combination of solidification and wiping. It's still under
Okay.
investigation.
Good. Good, good. So we learned a lot on the wiping process and how can we control the coating weight. And I have one last question for you. The more in terms of a final background for the ones that are just arriving in the business and started to get more involved with the galvanizing process because of your knowledge and your huge experience in what we do. If you could advise them in what they should learn, what they should pay more attention in terms of the future for this business, what would you say?
Please join the zinc coating group. You see that very exciting about that. I'm there for more than 40 years now. Indeed, galvanizing light is a very wide domain. Wiping is only a small part of it. There are many processes involved, from welding, annealing and its metallurgy, heat transfer, wiping, skin pass, post-treatment. So wiping is only one part of that. And there are many things to investigate, to address, and to tune. Many domains like fluid dynamics, heat transfer, mechanics, chemistry. You address more or less all the topics of the scientific topics. The processes are complex and interdependent. This is maybe something that's very, very interesting to keep in mind. When you see a defect at the exit, you never know exactly which process is responsible. The aspect of the defect is not immediately correlated to a specific equipment. And it means that this is going to take time to link also the different process, but also the constraint. You are running thick strip at low speed. Thick strip are usually heavy coatings. The steel are not the same, and so on. Some you may have hot rolled in some case, and this requires experience. Now is coming new challenges. We have new coatings with the
That's
zinc
true.
magnesium today. That's coming. There is not one single zinc magnesium. There are many types. It's not easy to link all of them. We have CO2. We have complex equipment and model. High metallurgy is high, new process like pre-oxidation to improve wettability. So it's very interesting for scientists, and I wish that experts will be recognized in future compared to managers, because it really takes time to become expert.
It's true. It's true. What else, Michelle? What else you would like to say to the ones that are watching us?
Well, some final word. If you are a PhD, for example, those PhDs, as I was when I was young, you know everything, but unfortunately nothing is working. That's why we need engineers to go online. When you talk with operators, everything is well working, but they are not able to explain you the reason of that. See? So this is where you are really. You are there to solve the problem. I mean, when nothing is well working and nobody knows why, this is why you have to clarify. There has been also a lot of improvement along the year, but keep in mind that success is a function of knowledge and product and equipment. And the question is, how high will be the X value? How high is the knowledge compared to the equipment? Some people claim that it's over 0.7. So it means knowledge is very important.
For me too. Okay, Michelle. Thank you. Thanks a lot for your time. Thanks for sharing your knowledge with us. For those who are, like I said, new in the business, I think they have learned a lot based on everything you had shared with us. But before we close this chat, if anybody would like to reach out to you with more questions or perhaps try to learn more from you, can you tell us how could they find you?
So I'm still working a little, that's clear, even I'm retired, at least for the next maximum 5 years, I think. So in case you have questions or you want some technical assistance, you can contact me through my email, and I can give quick answers if you present yourself and your problem clearly. I can share all the papers that I wrote previously, and I'm also doing for those who wish some web trainings, and they are always tuned to each customer. That's it.
That's
Thank you.
good. Again, thank you so much. Thanks a lot for being here, for everything you have told us today. For me personally, it's really a pleasure in having the opportunity of getting to know you more and how much you have done over your career. Thanks a lot.
Thank you.
With this, we are closing this session. For our audience, I would like to tell you a bit more of what you can expect in our next episode. So we'll be speaking about zinc path management. So keep yourself tuned for what is coming. This is what we have to tell you today. I hope you have enjoyed everything you have learned. And I look forward to see you again next time. Thank you. Bye-bye.